Hello, geometry scholars. Today, we are going to be doing secant and tangent theorems. So these theorems are actually kind of useful, concrete situations that you may see on things like the SAT and the ACT. And these theorems are, really nice to know, and we will kind of see them in action. So just to kind of review here what a secant and a tangent are. So a secant line basically connects, two random points on the circle and then extends beyond the circle. So that is an example of a secant line. And you can draw this example in your notes. And then a tangent line, we have kind of discussed in class the idea of going on a tangent. Going on a tangent, which means that if somebody's talking about going on a tangent, that means that they are talking about something that's kind of related to the topic, but it's off topic. And the tangent line kind of goes into the circle, but doesn't. It just skirts the outside of the circle at a point. So that is a tangent line. All right, so you're going to see two cases today on Delta Math. Case one is a secant intersection outside of a circle. So what the solutions on Delta Math are going to do, they're going to kind of guide you into just kind of the initial setup that is pretty consistent. So the good news is that we'll call this first secant line A, and we'll call this part B. So the outer part of a secant line we call A, the inner part of a secant line we call B. And then with the other secant line, we'll call this C and D. And just to be super illustrative with color, and I absolutely love color marking, if we want to think about the total secant line, I will make that in dark blue. So the total of the first secant line is referred to as A plus B, and the total of the second secant line is referred to as C plus D. And basically the formula that is used on your Delta Math, so to speak, to solve this sort of situation is to do, for one secant line, you do A, so the outer part of your secant line, times your total, which is A plus B, equals to C times C plus D. So we're taking the outer part of the secant lines and then multiplying by the total secant line. And I'll even just kind of like make a note here. So that is the total secant. And then the C would just be the outer part of the secant. All right. So then we are going to go to the secant tangent outside of the circle problems. So now we're going to go to number 2, which is the other case. So this is the secant tangent, and it's called secant tangent because this line is the tangent line. And we'll call this A, and then we'll call this part B and C, where on the secant line, the total secant line will actually be B plus C. Oh no, here we go. And we'll just call that B plus C. And we can actually see that this is kind of a similar case on this one, except what is going to be different is how we treat the tangent line. So the tangent line will actually be a squared, and it will be equal to b times b plus c. And these are the two general formulas that are useful today. Please make sure that this is front and center on the top of your notes, because we will be continuously referring to this formula. All right, so let's kind of look at these examples solved out now. And then we'll kind of see one more example of the secant tangent. So example one is the two secants intersecting. So the formula for this, I'd just like to kind of mark A, B, C, and D. And our formula for this is A times A plus B equals to C times C plus D. And then I can just go and plug in from the diagram. And what's nice is that I have the A, and then the B is the X. So that total of the secant line is that 8 plus X. And then on the other side, I'm going to do 4 times 4 plus 34. And I'm just going to distribute. So I get 16 plus 8x. And now we're just going to solve for x. And I see I got 16. And then I got 4 times 34, which is going to be 68 times 2. And it is getting a little bit late for me, so I will just go to my calculator and see what that is. So that's 136. So I got 16 plus 8x equals to 152. So I'm going to subtract 16 on both sides. So I get that 8x is equal to 152 minus 16, which is 136. And then I'm just going to divide by 8, and I'm going to get 17. And one question that you may be thinking about here, notice that 8 is, kind of twice as big as before. And we actually see also that 34 is, twice as big as the 17. So that is maybe a interesting pattern as well. But I do suggest kind of just sticking with the formula and kind of working off of that and labeling your A, B, C, and D on these. Okay, so let's go to the next one. So let's actually take a look at a tangent line problem now. So this is a secant tangent, a secant tangent, as they say in French. I don't know if that's really how they say it, but it is what it is. And I'm going to label this A, and then I'll call this B and C. C is kind of referring to the inside of the secant. B is referring to the outside of the secant. And the A is the tangent, the tangent. So I'm going to write A squared equals to B times B plus C. So on this one, I got 12 squared equals to 3 times 3 plus x. So that gets me to 144. And I got 9 plus 3x. So I'm going to subtract 9 on both sides. So I'm going to get 135 equals to 3x. And when I divide that, we get 135 divided by 3 for a grand total of 45. And then let's just do one more as well. So we do example 3. This is a secant tangent problem, like before. So we got secant tangent, and I'm going to do the same sort of labeling. So this is going to be the a squared equals to b times b plus c. So that's our a, our b, and our c. So I'm going to write that as 4 squared equals to 2 times 2 plus x. We get 16. Equals to 4 plus 2x. So subtract 4 from both sides. And I'm going to divide by 2. And I get that x is equal to 6. So I really suggest for all these problems, just start with theorem first. Start with that setup. And then just make sure that you are reading the information from the diagram and solving for x just as they are asking you to.